Hello students. So this is the part of the numerical methods. So in this part we are going to discuss solution of polynomial and transcendental equations. First we discuss why we are using numerical methods to find the solution of polynomial and also transcendental equations. Okay. So here I take one polynomial example x square minus 3x plus 2 equal to 0. So this is the polynomial of degree 2. So this polynomial, the solution of this polynomial we can find very easily by factorization. That is, this we can write as x square minus 2x minus x plus 2. Okay, x square minus 2x minus x plus 2 equal to 0, and this again we can express as a linear factors x minus 2 into x minus 1 equal to 0. From this the solution is x equal to 2 and x equal to 1. This is what we call by factorization. Okay, sometimes if the factorization is not possible to any given polynomial, then we use the formula x equal to minus b plus or minus square root of b square minus 4ac divided by 2a. By using this formula we can find the value of x. Okay, so these methods are the analytical method, that is basic methods. Now there are some polynomial where the degree of the equation greater than 2. So this is the equation of degree 2. Suppose we may get the polynomial of degree 3 or 4, 5. So when we go some higher degree polynomial, then it is not possible factorization, right? And also not possible by using the formula. That means when we go for higher order, higher degree polynomial, it is not possible by ordinary methods. Okay, so therefore in such case we apply the numerical methods. This is the one reason. And also this is for polynomial, and the transcendental equations are, suppose the equation containing the logarithmic functions, for example log x plus e raised to x equal to 0. So this is the equation containing logarithmic function and also exponential function, and also some equations may contain like cos x plus sin x equal to 0, some trigonometric functions. The equations containing logarithmic, exponential and trigonometric functions, so these equations are called transcendental equations. Okay. Now for such transcendental equations we cannot apply any analytical methods, so even in such case also we apply numerical methods. By applying the numerical methods we find the solution or the value of x. Okay, this is the reason. Now so in these numerical methods, the one point is the solution what we are getting, that is the value of x, so which is approximate solution, approximate answer we are getting. Okay, for any solution by using numerical methods we get the approximate solution. Okay, so approximate means which is near to the exact value. This point you please remember. The next point is in this in these numerical methods, so there is one important definition which we are using in the process. So that is called iteration process. It is called iteration process. So this is important definition in the numerical methods. Then what is this iteration process? So this is the process where we use the numerical methods repetitively. We apply the methods repetitively. That means we apply the method again and again to get the better approximation. Okay, so iteration process is what we apply the numerical methods again and again to get the better approximation. This is called iteration process. And the one more point in the iteration process, we get the better approximation by applying the method again and again. When we are applying again and again that method by using the previous value, for example, the first value of x, we get the approximate answer that I denote as a x1. X1 is the solution of the given equation. We get some answer, right? Then this is the approximate, which is near to the exact value. Okay, then what we do, we apply the numerical method again. We get one more value of x that I denote as a x2. Now here we can say that x2 is the better approximation than x1. Better approximation than x1. Okay, then again I continue the same. We get the one more value of x that I denote as a x3, and now we can say that this x3 is the better approximation than x1 and x2. Okay, likewise we continue the process till we get a better approximation. Okay, so here what we do, to find x2 we use the previous value. With the help of this x1, we use this x1, we get the better approximation x2. Then in the next step, to find the x3, we use previous value x2 and we get another better approximation than x2. Likewise, by using the previous value, suppose if you are finding x4, we use x3. Okay, by using the previous value we are getting the better approximation, and this process what we call iteration process. Okay, this is what we are using in the numerical methods to find the solution of transcendental equations and also the solution of the polynomial which is having degree greater than 2. Even we can apply for this second degree polynomial. If you have more degree greater than 2, we apply the numerical methods and we get the better approximation. Okay, and also one more point I explain here about this iteration process. See that this is the real line, and assume that for any transcendental equation or any polynomial, this is the interval 1 to 2. Okay, this is x equal to 1 and this is x equal to 2. Okay, and suppose the value of x means the solution of x, or we can say the root of x, the root of the equation, that is x value, is 1.5. Okay, between 1 and 2 Just assume that for any given equation, okay, the value of x is, that is a, we can say this x equal to 1.5 is the exact value. This is the exact value of x, 1.5. Then what we do, we apply the numerical method once, we get, as here I explained, we get x1. X1 is what? It is the approximate solution. Approximate means it is near to the exact value. Just assume that exact value is 1.5. Either the root lies this side or this side. Okay, we consider somewhere here. Okay, so this is, assume that this is 1.7. I applied numerical method once, we get x1 equal to 1.7. This 1.7 is the solution or is the root which is a near to exact value. Okay, 1.7 we get. Then using this 1.7 x1, we apply the numerical method again, we get the one more value of x, that is x2 we say. That x2 is 1.6. Okay, x2 is 1.6. Clear? So this 1.6 is very near to 1.5. So we can say that 1.6 is a better approximation than 1.7. Okay, obviously, so seeing this real line, this 1.6 is very near to 1.5 compared to 1.7. Okay, so similarly, we apply the numerical method again, we may get one more value of x that we denote as a x3. It may be 1.589, something in terms of decimal places, 1.589. Okay, this is between 1.5 and 1.6. So here one x3 is 1.589. So this 1.589 is a better approximation than 1.6. So we say that x3 is a better approximation than x2. Okay, so likewise, when we apply the method again and again using the previous value, we are getting very near to the exact value. Okay, so this is what we call iteration process. Clear? So this is what, from we are moving from one point to near to exact. Okay, by applying the numerical method again and again. This is what we call iteration process. Now the next part of this discussion is fundamental property. Is fundamental property. Now, to find the roots of any given equation, we first apply this fundamental property. First applying the fundamental property, then we use the numerical methods. Then what is this fundamental property? See, if f of x equal to 0 is a given equation, okay, f of x equal to 0, suppose this is the given equation, then there exist two values, a and b, such that f of a less than 0 and f of b greater than 0, then there always exist at least one real root, then there always exists one real root in the interval a comma b. This is called the fundamental property. See, suppose f of x equal to 0 is the given function. It may be a polynomial or it may be a transcendental equation. Then there exist two values a and b such that f of a is less than 0. Less than 0 means it is a negative value. Then f of b is greater than 0 means it's a positive value. If this is the condition, then there exists at least one real root in the interval a comma b. That is nothing but in the given function f of x equal to 0, what we do, we start from some values of x. We substitute the values of x in the given equation. Okay, suppose at x equal to a, this is the some value of x. I substitute in the given function. Okay, after substituting x equal to a, the value of f of x at x equal to a is negative, that is less than 0. Then I take the next value of x, I put x equal to b in the given function. Then at x equal to b, the value of the function is positive, that is greater than 0. See that again, at x equal to a, the value of the function we get as a negative. At x equal to b, the value of the function as a positive. The one should negative and one should positive. Then we can say that the interval is a comma b. Then the root of this equation lies between a and b. The root of this equation lies between a and b. This is the interval first we find, where at x equal to a, the value of the function is negative. At x equal to b, the value of the function is positive. Then we consider this a, b as an interval. Then when we apply the numerical method, the value of x we get between this a and b. Okay, this is what we call fundamental property. Okay, I just take one simple example to explain again this fundamental property. So for any given function f of x equal to 0, what I start as it is suggested that always you start from x equal to 0. You start the problem by putting x equal to 0, then you put x equal to 1, then you put x equal to 2, 3, 4, like that you have to continue. Okay, now first I put x equal to 0 in the given function. It may be a transcendental or polynomial. When I put x equal to 0, suppose the value of the function we get as a negative value if we get. Then I take the next value of x, put x equal to 1. Suppose the value of the function is again negative. If both values are negative here, then we must continue by taking next value of x. Take x equal to 2 in the given function. Suppose the value of the function is positive. If we get the positive value, then we get the interval. By fundamental property, at one value of x, the value of the function must be negative. For other value of x, the value of the function must be positive. Therefore, our interval is 1 comma 2. Okay, don't take this 0 and 2. Even if you take 0 and 2, you can get the answer, but the length of the interval is minimum. Okay, like here I just explained, taking the real line, suppose this is 0, this is 1, and this is 2. See, instead of finding the value of x in the interval 0 comma 2, so this is the big difference, the distance is more, okay, the length is maximum. Instead of taking in this length of the interval, if you find from this 1 to 2, okay, now the length is reduced. For instead of taking 0 to 2, if you take from 1 to 2, the length is reduced. In this interval we can find the value of x easily. Okay, so at x equal to 1, value of the function is negative. At x equal to 2, the value of the function is positive. Okay, this is the interval. Suppose at x equal to 2 is again negative, then we have to continue this at x equal to 3. If we get the positive at x equal to 3, now our interval is 2 comma 3. Okay, so here a equal to 2, b equal to 3, this is our interval. The value of the function at one value of x must be negative. For other value of x, the function of the value must be positive. So we are taking this our 2 comma 3 as an interval. So this is called the fundamental property. So before applying the numerical methods, that formula, we first apply this fundamental property, we get the interval. With the help of this interval, we apply the numerical methods. Okay, so now in the next video we discuss about the numerical methods to find the solution of a polynomial and transcendental equations. Thank you.